Hello and welcome to this video presentation by Legend Brands. My name is Brandon Burton, the Technical Education Manager for Dry Ease Products, a part of Legend Brands. Today, we're going to discuss the general drying process as it relates to structural restoration. We'll discuss dehumidification technologies, heat drying applications, and restoring a structure as cost efficiently as possible. The overall drying process requires an understanding of humidity, airflow, and temperature as they each relate uniquely to drying applications. The balance of humidity, airflow, and temperature is not an equal entity throughout the entire drying process. Depending upon the type of moisture present within the building by its concentration and the types of building materials, the amount of airflow, humidity, and temperature will vary from one stage of the project to the next. Initially, in most restoration projects, surface water will be the first water to be tackled by the restoration technician, followed by free liquid water contained within the building materials. Finally, the restorer will tackle the bound water held deep within structural materials. During this stage, the importance of air movement is dramatically diminished. The importance of a lower humidity and the presence of the appropriate amount of energy become exceedingly important. The focus of the restoration technician, in order to minimize the cost of the project and maximize drying performance, should shift as we move from the constant rate to the falling rate. We should focus on a high amount of air movement initially on the project, ensuring high velocity of airflow in order to excite and remove moisture from the surface of the building materials. However, as surface water is no longer present during the falling rate, this movement of air no longer directly influences water or water vapor. At this point, it's critical to ensure a much lower humidity, known as a low vapor pressure, to allow the transfer of water vapor from within the building material. To excite the amount of moisture that is in the building material in this later stage, it is important to ensure that an appropriate amount of energy has been applied to the structure to increase the vapor pressure present within the building material. In this graph, we can see how the rate of moisture loss from the building material is very rapid during the constant rate. Here, moisture content numbers will drop significantly during the drying process. As we move into the falling rate, however, it's characteristic of most building materials that the drying rate will begin to significantly retard and slow. If the appropriate adjustments are not made through the drying process, this slope will be very representative of most building materials. Here, we can see that the drying slope is much steeper during the falling drying rate, resulting in a much faster overall drying time. This is the impact of properly managing the reduction of air movement while focusing on a lower humidity within the structure, and as appropriate, ensuring an appropriate amount of energy has been applied to the target building material. There are several drying technologies available in the industry today to facilitate the conditions that we've just discussed. Understanding these predominant technologies and their best applications will yield the best overall drying process. Ideally, the project will be managed between 20 and 30 degrees centigrade. This is important to ensure that there is enough energy present to allow air to transport water vapor. However, if the temperature is allowed to far exceed 30 degrees centigrade, then additional issues can be generated by the high heat and temperature and the exceedingly high vapor pressure that can be generated. We'll discuss this in greater detail later. The predominant drying technologies in the restoration industry are the standard refrigerant dehumidifier, the low humidity refrigerant dehumidifier, sometimes called an LGR, Desiccant dehumidification, and heat and air exchange. Overlaid onto this psychrometric chart, we see within the ideal drying range the area of maximum performance for each technology, beginning with the standard refrigerant. We'll note that the standard refrigerant dehumidifier performs best in exceptionally high humidities and in warm and/or hot conditions. This is true because the standard refrigerant dehumidifier removes water vapor from air through the process of condensation. Adding energy causes water to evaporate. The reverse is true when using a refrigerant dehumidifier. Removing energy from that same air will cause the water vapor to condense. For this reason, standard refrigerant dehumidifiers prefer air to be at or near its point of saturation. The higher the water content and the greater the water content, the better the performance of the machine. Desiccant dehumidification systems, on the other hand, have a very opposite performance characteristic. As opposed to relying on condensation from very humid air, desiccant dehumidifiers utilize a chemical attraction to water vapor, commonly referred to as adsorption. This process allows desiccant dehumidifiers to remove water vapor from air that is already relatively dry. However, desiccant dehumidification systems have a point of saturation. In other words, the material that is used to attract water vapor can only carry a certain amount of water vapor at a time. This prevents desiccant dehumidifiers from being highly efficient in higher humidities. In other words, as humidity increases, they do not necessarily increase in performance, and especially as it relates to power consumption, become highly inefficient compared to other technologies in the rate of water removal in high humidity environments. Heat and air exchange is a new technology to the industry in terms of the focus and the amount it's being used. However, it is one of the oldest technologies for drying known to man. Heat and air exchange systems rely upon the water content of outdoor and surrounding air during a drying process. When outdoor conditions are exceptionally dry, this can lead to a very efficient and very effective drying process. However, if the outdoor conditions do not have readily available low humidity air, then a heat and air exchange system will draw in moisture-laden air from the outdoor environment. This can significantly slow the drying process, and it can also lead to exceptionally high vapor pressures within the structure. Drying under a high pressure environment, as we'll look at later in this program, can lead to water being driven deeper into building assemblies. This can be problematic in the form of microbial growth, slow drying, and other forms of secondary damage. Low humidity refrigerants, also known as low grain refrigerants, bring a very broad range of performance characteristics. We'll discuss the technology in a moment. However, this technology allows this form of refrigerant dehumidifier to perform in a much broader range of humidity conditions. It brings the benefits of the refrigerant dehumidifier's performance in high humidity down into the range of the desiccant dehumidifier, allowing for significant performance in a much drier condition. This allows the low humidity refrigerant to have a much more universal application in terms of structural drying applications. This is particularly important when understanding that the drying environment is going to move through constant and falling rate conditions. In other words, many projects begin with very high humidities and would call for refrigerant technology. As the structure begins to dry and we move into the falling rate, the performance characteristics of a desiccant in lower humidities become advantageous. Prior to the invent of the low humidity refrigerant, this would commonly call for the use of refrigerant dehumidifiers to begin many projects where desiccants would become advantageous during the latter stages. The low humidity refrigerant, however, bridges this gap and allows a single dehumidifier to perform well across the entire drying process. In order to better understand the performance differences that we've just discussed, it's important to take a closer look at dehumidification technology. We'll begin with the basic or standard refrigerant dehumidifier. Within a standard refrigerant, there are two coils, represented here in blue and red, called an evaporator and a condenser. Air from the drying environment is presented to both of these coils, beginning with the blue and then the red. The purpose of the first coil is to cool the air to below its dew point temperature. However, if the air is exceptionally warm or the humidity exceptionally low, then it is improbable that the air will be cooled to its dew point. This is the reason that a basic refrigerant prefers air near saturation. This is air that it's near its dew point. The second coil within the refrigerant dehumidifier then reintroduces heat in the cooled and dehumidified air. This is to ensure that warm dry air exits the dehumidifier to support additional drying within the drying project. Here, utilizing a psychrometric chart, we can see what happens to the air as it passes through the refrigerant dehumidifier. We begin with a condition of 30 degrees Celsius and 40% relative humidity. As the air enters the refrigerant dehumidifier, cooling begins to occur as the air passes across the first coil. As the temperature drops, it approaches the saturation curve of our psychrometric chart. At 15 degrees Celsius, we achieve saturation, otherwise known as the dew point temperature. If additional cooling occurs as the air passes through the system, the additional cooling will result in condensation. As the line travels down the saturation curve, water is condensing onto the coil, and dehumidification has occurred. Low humidity refrigerants were commercialized for dehumidification in the 1990 to 2000 decade. There are a varying set of technologies used in low humidity refrigerants. One of the most common is a heat exchange core. Heat exchangers, commonly constructed of a corrugated aluminum or thermoplastic, allow energy to transfer between two separate air streams without allowing the air to mix. Low humidity refrigerants that incorporate an energy exchange core typically will utilize an airflow pattern much like what you see in this image. Warm, moisture-laden air is drawn in one direction through the exchange core. In the opposing direction, air from the cold evaporator coil is passed across the other side of the energy exchange plates. This allows the incoming warm, moisture-laden air to be pre-cooled through the exchange core. This allows for greater water removal and does so at a lower energy consumption rate. Here, utilizing the same psychrometric chart we discussed earlier, we can see what happens to air as it passes through a low humidity refrigerant. Beginning at 30 degrees Celsius and 40% relative humidity, as the air enters the air exchange core, the air is cooled substantially before the air is presented to the point where dehumidification is actually occurring. Represented by the dot at 22 degrees Celsius is the cooling that occurs through the block alone. This is the pre-cooling that occurs in the low humidity refrigerant. Now, the air is much closer to its point of saturation at 15 degrees Celsius. This ensures that as the air now passes across the point at which we are performing dehumidification, the cold evaporator coil, that we have a much greater capacity to drive the air to a condition below its dew point. This will result in a significant increase in water removal, especially in dry conditions, with again a much lower rate of power consumption. Low humidity refrigerant technology dramatically improves the performance of a refrigerant dehumidifier. Here we see a comparison between two similarly sized refrigerant dehumidifiers. In green, we see the performance of a low humidity refrigerant, and in orange, the performance of a standard refrigerant of the same size. The only difference between these two machines is the addition of the low humidity technology. At a high humidity, we see that performance is nearly identical. The only difference between these two machines would be the amount of power consumed. However, as humidity is decreased over time, moving to the right on the graph, we see that the performance of the standard refrigerant dramatically drops, while the low humidity refrigerant retains a much better performance. This is exceptionally true when we reach a condition of approximately 20 to 40% relative humidity. Here, the performance of the low humidity refrigerant is nearly double what we would achieve with a standard refrigerant dehumidifier. In summary, low humidity refrigerant dehumidifiers offer a broad range of performance benefits. First, lower power consumption is necessary to produce the same or more water than a standard refrigerant. Additionally, we have a significant increase in the amount of water the dehumidifier is capable of removing. Finally, lower humidities are produced by the machine, allowing it to perform in conditions significantly drier than refrigerant dehumidifiers are characteristically able to perform. Additional advancements have occurred over recent years, further improving low humidity refrigerant dehumidifier performance. These advancements include automated controllers that allow the dehumidifier to automatically adjust to changing conditions through the constant and falling drying rate, onboard monitoring to speed the process of environmental monitoring and also increase the accuracy of data obtained, higher airflow for better circulation throughout the drying project, lower weight to ensure for an easier transport, and a smaller size. Low humidity refrigerants provide nearly 80% more water per kilowatt of power consumed than a standard refrigerant dehumidifier. However, the performance increase per kilowatt is significantly greater when we discuss desiccant dehumidification. As discussed earlier, desiccant dehumidification systems do not rely on condensation for water removal. In essence, they attract water vapor much like a magnet would attract metal, using a low chemical vapor pressure. They're very effective for this reason in low humidity environments. However, they require a very high power usage for the amount of water removed. This is because a heater must be used to reactivate the silica gel or lithium chloride that the desiccant is based upon. High power due to the heat reactivation means that significant increases or losses in energy efficiency are important to consider when looking at desiccant dehumidification. In addition to the high power consumption of the desiccant dehumidifier, it's also important to remember that the silica gel or lithium chloride has a limited capacity to transport moisture. As the rotor in this image revolves approximately 1 time per minute, it has a limited ability to carry moisture into the reactivation phase. If water is evaporating at a greater rate than the rotor can carry and transport moisture, then humidity will continue to increase over time. The only way to compensate for this is to use exceptionally more dehumidification than would be required had a refrigerant dehumidifier been chosen initially. This overcompensation in dehumidification further exacerbates the issue with the overuse of energy during the drying process with desiccant dehumidification. In projects where evaporation rates are slow from primarily just dense materials on the structure drying project, desiccant dehumidifiers can be an ideal choice. However, whenever highly porous materials are present or high degrees of saturation, desiccant dehumidifiers do not provide the efficiency necessary to properly manage the restoration project. Finally, we discuss heat and air exchange drying, otherwise known as heat or high temperature drying. These types of drying systems typically utilize a constant, fresh supply of outdoor air and the addition of heat to create a drying environment. Whenever outdoor air is used, with or without heat, it's important to ensure that the outdoor air is drier than what can be created using the mechanical dehumidifiers we've just discussed. We also need to ensure that the outdoor air is readily accessible to the project. If the outdoor air is accessible and dry, it must also be stable. Changing weather conditions can rapidly reverse the conditions that made the outdoor air acceptable. In addition, whenever outdoor air is accessed, we must also ensure that we address building security. Finally, the customer must also be consulted. Anytime a restoration project utilizes outdoor air, doors, windows, or other access to the outdoor air must be allowed to maintain that access. If a customer or occupant is unaware or disagrees with this type of configuration, we can easily lose our ventilation to the outdoor environment and all humidity control. Although heat or high temperature drying can be very advantageous, it can also be disastrous. If utilized when the outdoor humidity is high, we will create exceptionally high vapor pressures within the drying environment. Especially when there are cooler surfaces within the environment that are not properly heated, condensation can occur. Cavities and voids, if not ventilated, can also receive an increase in water vapor and secondarily allow for damage on previously unaffected building materials. This occurs because temperatures are not stable and constant throughout the environment. Even if we have an exceptionally high temperature in one space, such as within the drying space, interstitial cavities and voids, unaffected areas, and other parts of the structure will be cooler. When this air that is exceptionally warm with water content is allowed to move to cooler areas, the capacity of the air to support water vapor will decrease. And much like making a container smaller, eventually the same amount of water will begin to overfill the container. This will lead to condensation and secondary damage. These containers are an exact representation of a psychrometric chart. Here we can see that at warm temperatures, the chart has a very high capacity for water vapor. However, as temperatures are made cooler, the chart begins to decrease in its capacity for water vapor. This is what will occur if high temperature, moisture-laden air is allowed to move towards or into cool surfaces and areas. As it loses its capacity to retain water, e.g. its energy, eventually high humidities and condensation will occur. In this image of a basic structure, we can see how heat application will not be universal throughout the drying project. Represented in red is the highest temperature air influenced by the direct addition of heat to a space. However, as that air comes into contact with building materials, the heat resistance value of those materials will prevent even energy transfer. In all of the neighboring spaces represented in orange, we see spaces where a cooler temperature will exist. Water vapor in the area in red generated by drying and evaporation will move into these spaces. As the air moves into these spaces that are cooler, the humidity relatively will increase, and condensation and secondary damage become an exceptional possibility. The primary concern with these areas now highlighted in red is that they were not affected initially, and because they were not affected, they are not being monitored by the restoration technician. Moisture driven to these spaces by the high temperature and vapor pressure are now going to allow water vapor to condense and absorb into these unaffected materials. They'll go unchecked and undiscovered and cause secondary damage that will be discovered in the future. The advent of low humidity refrigerant dehumidifiers dramatically changes dehumidification technology. Low humidity refrigerants now offer the greatest range in performance of all available technologies in the industry today. They also remove water with a lower overall power consumption. Desiccants continue to be the performer they always have, however, in a limited capacity. Desiccant dehumidifiers, because they saturate on the silica gel or lithium chloride, are not the ideal dehumidification system during the constant drying rate, which most projects will encounter. However, in projects where only dense materials and low humidities are present, they continue to be an ideal choice. Heat, however, as a drying process, continues to be advantageous when we have access to exceptionally dry air on the exterior of the structure. This allows for the use of outdoor air while maintaining a low vapor pressure in the environment and preventing the push of water vapor within the space to uncontrolled areas where secondary damage can occur. Thank you for joining this presentation from Legend Brands on dehumidification technology and best drying practices.